Hey everybody, and welcome to McArdle Math Academy. In this video we'll be talking about volumes of revolution, and we'll be doing one example. Let's talk about distances on a graph. Alright, so here's the graph of y equals x squared, and I have plotted 4 points. So what happens is you take the x value, x equals 3, you use the function y equals x squared, and we find out what that value is. Alright, so we get 9. So it's pretty easy for a general x value over here to find this distance. If I just wanted this vertical distance for a general x value on the x-axis, we would plug it into the formula that we're given, so we know that this distance is x squared. But it's a little bit trickier. Let me get a different color. It's a little bit trickier when I take an arbitrary y value and I want to know what this distance is. Alright, well, the same formula for the function can be used. So let's look at 16, for example. 16 is the y value. When I go over to find the x value, I find that this distance is 4, because that's 4 squared is 16. So what we have to do is take the function, y equals x squared, solve it for x, and that's going to give us the rule, which will tell us what this arbitrary distance is for any y on the y-axis, so it'll be the square root of y. And we're going to need to have this kind of back and forth relationship here when we work through problems involving volumes of revolution, depending on which way we're rotating our region. Alright, so let's look at an example. Alright, so the example we're going to look at is to find the volume when the region is rotated about the y-axis. And I haven't given you the region yet, so let me draw a region for you. So we'll look at this red region bounded by the graphs of y equals x squared, y equals 16, which is this horizontal line, and x equals 0, which is essentially the y-axis in this case, or in every case. So now that's our red region, and we're going to be rotating about the y-axis. Alright, so we think about taking this region and spinning it about this axis, and what you're going to end up getting is, so you'll see the same shape here. Here's the red region that we have, but it's going to be rotated. So here's the axis, and it's going to form a little bowl. Now the bowl will be a solid bowl, and it'll look just like this. Alright, and that's what we want the volume of. So what we're going to do is we're going to take a slice, and our slices are always going to be drawn perpendicular to the axis of rotation, so the slices here will be horizontal slices, and they're each going to have a little thickness, a particular thickness, which in this case we have as dy, since that's the y-axis. So that little thickness there is dy, and they're going to have a volume. All right, so each of those slices will have a volume. And if you think about the slice, it's a circle that has a thickness. So when we want to find the volume of a circle, we need to know what its radius is. So in other words, I need to know the distance from here to here, and we're going to call that r. Alright, so the volume of my slice in this case is the area of the top of the disk, so that's pi r squared, times the thickness of the disk, which is dy. And now every time you get this little formula, you want your variables to match. So you want r to be in terms of y. So what we do is we come back to the original graph, and especially we come back to the two-dimensional picture, and we look at what our r is represented on this two-dimensional figure, and that would be this distance here. Alright, and this is a case where now you have to take the function y equals x squared and solve it for x. So therefore that radius is always going to be the square root of y. That's that distance. No matter which y value we start at, it's going to be the square root of y. So that's what we're going to set as r in this case. Alright, so we come back over here, and we have pi r squared, so that'll be pi times the square root of y squared dy. Squaring that, we just get pi y dy. And that's the volume of our slice. Alright, once we have the volume of the slice, we set up the integral. Alright, and we have the volume of the slice on the inside of the integral, because we're summing up all of these disks as y ranges from 0 all the way up to 16. Now how did I get those bounds? Well, you look back at the region, you look at the smallest value of y, which is y equals 0 down here. Then you look at the biggest value of y, which is 16. So we're going to take slices as we move through this region. And then we sum all those up with infinitely thin slices, which gives us our integral. All right, so we come on back to our integral. It's pretty simple. We just apply our basic rules, pi y squared over 2, and we range from 0 to 16. So we have 16 squared over 2 times pi, and that'll be our final volume of this solid bowl. So let's pan out so we can see exactly all the steps we took for this problem, and the things I wrote in green are really the trickiest parts of the problem. Alright, hopefully this helps, and check back for more videos later. Thanks.